Okay, our next talk is Share the MAYO, Thresholdizing MAYO by Sofia Selly. Is that correct, Selly?
Yes.
Sofia Selly, Daniel Escuerdo, and a name that's more difficult for me.
It's fine. I can pronounce them. Don't worry.
Okay. So Sofia Selly is presenting.
Yes. So thank you very much. So yes, this is a work that we created with these three authors that you see here. So this is a co-authorship of a publication with Daniel Escudero and Guillem Niot. And if you're interested in actually reading the full version of the paper, I invite you to click on this specific link on the slide and read it fully if you're interested. But essentially what we wanted to present in this paper is kind of presenting a scheme and the ability to create a threshold version of OB-based schemes. And you will see later what specifically we defined as OB-based, but essentially are the schemes of the form as, for example, MAYO or UOB. So why are we interested in this is because recently there has been some renewed interest in actually providing threshold cryptography. Why is this so? Because it is an emerging field in cryptography that provides many real-world applications by allowing the distribution of signing power to several parties. And there are many real-world applications that are trying to use threshold cryptography because it does provide really nice privacy-preserving properties. The most practical schemes that currently exist that arrive to really nice computational and communicational complexities, unfortunately, are only set in the classical setting and are usually set by providing specific schemes that are worked over ECDSA-based signature schemes or Schnorr-based signature schemes. And what we wanted to actually see in this paper, if there's the possibility of providing a threshold version of some of the post-quantum schemes that are currently being proposed as part of the post-quantum NIST competition. Why we're interested in this is because even recently, the National Institute of Technology and Standards of the United States have recently actually published a specific document that is kind of like a call for threshold schemes. And one of the core properties that are interested on this specific type of schemes is that they have the property of quantum resistance. So it seems that from both standardization bodies and also from the industry perspective, we are interested in providing some sort of threshold schemes for the post-quantum signature schemes. Okay, so with everything, we didn't start in the vacuum, but rather we started by looking at the state of the art or the literature that exists in general about threshold signature schemes. And our starting point is going to be the work of Gozzo et al. That was a publication that happened in 2019. What essentially those specific researchers did is that they looked at the state of the art at the point of the NIST post-quantum competition. So this was the second round of the first NIST post-quantum competition. And what they look is that if any of those post-quantum signature schemes have the possibility of being thresholdized. And one of their conclusions was that the specific family of cryptography, of post-quantum cryptography that is called multivariate quadratic-based cryptography, seems to be the one that is more feasible to thresholdize. Why? Because it mainly involves the majority of operations are going to be matrix multiplications. So it seems to be that is the one that is much more easy, quote unquote, to create a threshold version of. Because of this, what we wanted to do is then to focus on this specific family of post-quantum cryptography, which is the one that is called multivariate-based post-quantum cryptography. And because we're interested in actually providing a scheme that seems to be practical, we decided to focus on what we call OB-based schemes. So those schemes that are based on the specific signature scheme that is called the oil and vinegar signature scheme. And we exactly focus on UOB and MAYO. Why? Because there seems to be that those schemes are the ones that are really practical because they provide great communication and computational complexities, and also because they seem to be tailored and feasible for real-world applications. Okay, so just like a little detour, let's maybe start looking at what this thing that is called multivariate-based quadratic cryptography is. Essentially, it is a mathematical problem in which we build cryptography out of it. So essentially, what you're going to have is that you're going to be having system of equations, so m equations. Each equation is going to be having the quadratic form, and it's going to be having n variables. So essentially, in these kind of schemes, what you have is that you have m equations in these systems, and then you also have n variables. Specifically, in the scheme that is called MAYO, you were also going to be having some specific different parameters. So you also will going to be having the k parameter and the e parameter, but those are specific for the instantiation of the MAYO signature scheme. If you want more of a traditional definition of what multivariate quadratic cryptography is, essentially is the one that you see in this slide, in which each one of the equations is going to be of the quadratic form, as you see here. And it's going to be having the three components that you see here. First, the quadratic component, then the linear component, and then the constant term. Essentially, all of the coefficients in each one of those components are going to be taken from the finite field. And this is kind of like the classical description of multivariate-based quadratic cryptography. In the more modern description, we really don't care about the linear component or the constant term, but we're just going to be focusing in the quadratic component. But essentially, that's how it looks like. There's another description that you can look at it, in which instead of looking at this system of equations, what you're going to be having instead is maps. A map that we're going to be calling P, which essentially maps from Fn to Fm. And essentially, the problem asks you that giving a multivariate quadratic map, this specific map P, over this specific finite field FQ, and a target T, it is to find a solution S, or the pre-image S, such that when you apply P of S is equal to T. So here you will see that we are already getting close to cryptography, because if you set that specific T, for example, to be the hash of the message concatenated with the salt, you essentially have a signature scheme. So that's where we base and construct cryptography out of this specific problem by constructing specific signature schemes. And it turns out that there's two big families that you can actually have in order to build multivariate-based quadratic cryptography. You could have the ones that are called usually pure random systems, which I think the next presentation is going to be talking about. Or you can also be the ones that we are focusing on this talk, which are the ones that are called trapdoor-based. And in that, you have the subfamily that I have already talked to you about, which is the one that is called the OB-based schemes. Okay, so what is this subfamily of the trapdoor base? Essentially, there's some kind of structural information on this specific public map P that will allow you to create a signature. But for everybody else that is looking from outside, that specific map P is going to be look completely random. So there's this hidden structure or trapdoor information that is going to be your secret key, and the trapdoor function is going to be your public key. We usually use a specific paradigm of cryptography to create the signature scheme, and that specific way of constructing cryptography is called the hash and sign with retries approach. Why with retries is because with some probability, sometimes you're not going to be finding a solution, so you have to set some variables again and try again. It turns out that in the single-party setting, that is completely fine to do. It turns out that when you actually want to do this procedure in the threshold method, that is going to be the most difficult procedure to thresholdize. Okay, let's look at OB-based signature schemes. Essentially, as I told you, this is a family that is based on the trapdoor idea. So what you're going to be having now is a linear subspace O, which is going to be your trapdoor or your secret key, such that when you take every vector of O, when you do P of O, is going to be equal to 0. And essentially, in these kind of schemes, what you're going to be having is tree procedure as any kind of signature scheme. You're going to be having the key generation, signature, and verification. In Threshold, we're mostly interested in key generation and signature. In key generation, essentially how you do it in this kind of schemes is that you first sample a matrix that we're going to be calling O, and then with that specific O, we're going to be creating our public key that we call P. Our P is going to be a really big matrix that is going to be having some sub-matrices inside. The two top sub-matrices, P1 and P2, are going to be chosen as random, and the specific third matrix that you see there is going to be computed with that specific equation. So here it's important to note that there's a direct relationship with that specific public key with the specific secret key that you just sampled. How does it look like in a more like matrix-like perspective? It looks like this. So this is precisely what I just described in the previous slide. Next, you're going to be having the signature procedure. The signature procedure essentially asks you to apply P of S is equal to the hash of the message and the salt. So you're essentially looking for that specific S. How you do this is that you first choose a specific V that we're going to be calling the vinegar variable, and then with this specific choice of V, you're going to try to solve that specific system, so that when you do P of O plus V, is going to be equal to P of V plus P of O plus the differential applied on V and O. Because you know this secret information, you can just eliminate the P of O because you know that it evaluates to 0. You already have set the V, so you could also have that as a constant. And then what remains is just a linear system of M equations in M variables. And again, this has a retry procedure. So if there's no solution, you just retry again. And your signature is just that, is S, which is the addition of O plus V. And again, in a matrix representation, it looks like this. First, you have the procedure in which what you do is that you build a linear system by the choice of B. And then what you do is that you try to find a solution if that solution exists. I already told you that in a single party setting, actually retrying, there's no problem, because it turns out that even if you're leaking some of the information, so for example, you're leaking the fact that you're retrying, or you're leaking the fact that there's some information that didn't lead to a specific signature, there's no attack that can actually exploit this specific information leakage, which is great in the single party setting. But it turns out that when you actually try to create a threshold signature out of this specific procedure, this is going to be the most complicated one. Why? Because it means that what you are going to have is a procedure that tries to solve a system or linear equation in which both the input matrix and the target vector are going to remain secret. So what you're going to be having is specifically this multiplication. You're going to be having A multiplied by X is equal to Y. But remember that the public key has a direct relationship with that specific secret subspace, right? It has a direct relationship with O. So you just cannot reveal in the clear this specific matrix A, because that will mean that over time you're revealing structural information of that specific subspace. So you have to do this in a way that you are masking that specific matrix A. So again, coming back to some of the previous slides, what we said is that we indeed look first as the state of the art. And the state of the art already provides us of kind of like a solution on how to do this specific procedure in a safe-ish way. But what we found out in our publication is that the procedure that they propose is indeed not safe. What they propose is two ways. Either you mask that specific matrix in the right, or you mask that specific matrix in the left. So what you do is that you sample a matrix, let's call this matrix S, and then you multiply the specific matrix A by that S. Or you can do the contrary, and you can indeed mask at the left side. So from a perspective of maybe information leakage, this is not really great, because it turns out that with some probability, as we say, some of the OB-based schemes are going to be failing and you have to retry. And when you retry, it turns out that you're revealing to all of the parties, in the first case, the image space of A. And as A has a direct relationship with O, this means that over time, you're leaking structural information of the O. In the case of left-side masking, essentially what you're doing is that you're leaking the kernel of A. So again, this procedure is not great because now you have a high leakage that arguably really appears insecure. We don't have a direct attack in the paper, but it is easy to see how this high degree of leakage can easily lead to some kind of abuse and essentially later guessing for that specific secret key. Okay, so here a little bit of interlude. I'm going to show you in the next slide a specific solution that we come up with, but our specific solution is set up in a specific model. The specific model that we work with is the Universal Composability UC framework. So this means that we actually don't set ourselves in a specific security model. We don't provide proofs, for example, for active security or for passive security or for dishonest or honest majority. But essentially what we provide is a mathematical proof that shows that the procedure that we're going to be showing has the lowest degree of leakage that we could possibly come up with. But later, what this essentially means is that we have some procedures that are really easy to instantiate in any security model because that specific instantiation is agnostic to any of the security models. Okay, so what is the specific solution that we come up with? Instead of only doing a right-side masking or a left-side masking, what we do is both. We mask both at the left and both at the right. And it turns out that with that, what we do is that we lower the information leakage as low as possible. And for all of the other operations, we can just apply generic MPC techniques. If you want to actually show that indeed this leads to a valid solution, you can actually expand the equations and see that even by doing these both sides maskings, we do arrive to a specific solution to the specific system of solving obviously the specific system of linear equations. Okay, so once that we have that specific procedure, now we can actually create a threshold signing procedure because everything else is just generic MPC techniques. So for example, for the specific creation of the shares of the secret key, you can use a trusted dealer or a distributed key generation. And for all of the other operations, you can also use generic MPC techniques. The only difference is that when you're actually trying to solve that specific system of equations, what you're going to be calling is the specific procedure that we just showed in the previous slides. It does mean that you do have a degree of leakage because eventually over time you are leaking both the rank deficiency of A and also the rank of A. But it turns out that the interval in which the rank of A lives is really small, so this is almost equivalent as only leaking the fact that a specific matrix A is rank deficient, which is already what happens in OB-based schemes in the single-party setting. So we don't arrive to a solution that is completely leakage-free, but we arrive to a solution that has the lowest degree of leakage, and we don't have a way to actually construct an attack that exploits this specific information leakage that this procedure has. So that's essentially how we do it. It is a little bit costly because now what you're going to be having is that instead of having one matrix multiplication, you're going to be having two matrix multiplication because you are indeed masking at both sides. So from a communicational perspective, we arrive at 9 rounds. And from a computational perspective, what we're going to be having is 2m plus 6 matrix multiplication. But this is not so, that's kind of like on average computation, because it turns out that there's some concrete optimizations depending on the security model that you can choose. So for example, let's say that you choose some dishonest majority. In those cases, you can use something as matrix triplets in order to be able to pre-process some of the matrix computations ahead of time, so that it is not so computationally costly. Or for example, let's say that you want active security. In those cases, instead of using directly zero knowledge or max, you could use, for example, distributed zero knowledge in order to, again, drive down the computational cost. So feature work that we're currently doing is now actually setting the specific security model that we want. Because of that, then we can actually set the concrete optimizations that we want to use in our scheme. And with that, we can actually provide a concrete implementation in C. Also note that as part of our work, we also provide a way to actually create a threshold verification mechanism, because there's some real-world applications that are not only interested in a single-party verification, but also in a threshold version of the verification procedure. So in this case, we also provide that because, again, OP-based schemes really are easy to instantiate in a threshold manner. OK, and with that, that's our work. So thank you very much.
Okay, do we have any questions? So you looked through this for UOV and MAYO,
Yeah.
and you were saying because of efficiency for those. What would be different about thresholdizing QRUOV, for example?
Oh, so any of the schemes that are based on OV-based should be easy to use the same kind of approach, because all of the ones that are actually built upon the oil and vinegar schemes actually follow the same kind of like procedures that I just showed. The ones that will be a little bit different are the ones that are based on random systems, because most of the times they're instantiated with a Fiat-Shamir paradigm, so that is going to be different. But for example, schemes as NOVA, MAYO, UOV, all of them could easily use the same techniques.
Okay, thank you. Are there any other questions? Okay, well, if not, let's thank the speaker again.